this morning that since we've now solved
Yeah, we can see
the
that.
problem of the demographic exoplanets, like move on to that for something that's easier. The demographics of life itself, clearly that, not just life, but eventually intelligent life. And as we look forward to the NASA program, for example, space-based program, there's certainly long-term goal to understand at least the questions of primitive life. How well can we find that? Then eventually, could we even find some evidence of intelligent communicating life? So that's the topic of the panel. Next slide, please. So I'm going to start off with just laying out first. The top part of the slide shows what's called the Drake equation. It's named after Frank Drake, who's a radio astronomer who has developed one of the very, very early searches for extraterrestrial intelligence from the Green Bank telescope. And this plaque here is actually on the wall in the Drake Lounge of one of the telescopes in Green Bank, where Frank first put together the Drake equation. And we're going to organize the talk and the speakers to track some of the different parts of the Drake equation, which starts out how many planets, how many Earth-like planets are, and Jessie Christiansen from NExScI is going to address that and some of the issues with getting to those terms in the Drake equation. And that's really the astrophysical part of the equation, to which we've been making spectacular progress in the last 20 years, well after Frank first posed the question back in the 60s. And then we'll have two speakers, Laurie Barge from JPL and Lisa Kaltenegger from Cornell, who will talk about this question of what fraction of those planets might develop life and where might we look for it. Laurie will talk a little bit about where we might look for them in the solar system, and Lisa will talk a bit about how we might find these around exoplanets. And then there are three terms, or certainly two fractional terms, a fraction of those worlds that develop intelligent life, and the fraction of those worlds where they actually are in a communicating phase. And then perhaps the most mysterious term of all is the lifetime of a communicating civilization. And Jason Wright, who's been leading a lot of efforts in technosignatures, will talk about that. So we'll start off with Jessie. The idea in the panel, will have each panelist will maybe give a little 5-minute pitch describing sort of their take on some of this, and then we'll get into sort of questions that either I'll pose or have members of the audience pose. So Jessie.
All right, thank you. You can pop to the next slide. So I really didn't realize until Chaz sent me the slides about half an hour ago that he wanted me to include the first term. That's the R star. This is the rate of star formation in the galaxy. Does anybody know this number? I had to look it up. What's the rate of star formation? It's like a handful of solar masses per year, 5. I Googled, and the AI overview was like 1 to 2 solar masses per year. And I'm like, haha, AI hallucinating again. I'm going to go and read an actual article. And the first 3 articles were 1 to 3, 1 to 5, 5 to 7. I'm like, we're missing some exponents here shortly. So then I pulled in the big guns. I messaged my husband, who is a galaxy formation theorist who works galaxies. And I'm like, Phil, what is the rate of star formation? And he's like, 1 to 3 solar masses per year. Oh my God. Okay. This blew my mind. I'm still reeling 18 minutes later from this. It's a very small number. We are saved by the fact, obviously, that the galaxy is billions of years old and we are in a quiescent part of star formation. It used to be much more bubbly than it is now. And now we have hundreds of billions of stars. But the rate of star formation is a handful of solar masses per year. Anyway. Okay. Second term, which is number of planets. Okay, so this is taken from the Exoplanet Archive a few days ago. This is on the x-axis, the amount of flux that a planet receives relative to Earth's flux. And on the y-axis is the mass of the planet in Earth masses. So Earth is at 1,1, and And then the points are colored by the temperature of the host star. So if you jump the next slide, thank you. I can also just try and drive. Okay.
I want to use this too.
Oh, brilliant. Look at this. Okay. So we have found almost 6,000 planets. In fact, some point this year, we will have hit this mark of 6,000 planets, which is very exciting. And as we've been talking all week, we are starting to be able to do demographics with this sample. It's challenging because there are many different techniques that each all have their own detection biases and different stellar selections that they point at. Come back tomorrow for my talk where I talk about how surveys are terrible and how we can make them better, more importantly. But the point is we now know of thousands of stars, and demographics are difficult, but we're doing it. And now we have an idea of the rate. Okay, so I'm going to break this down into two different bits, right? One is the very anthropocentric Earth 2.0. What is the rate of Earth-like planets? And by that, I mean rocky planets in the habitable zones of sun-like stars. So I've already really narrowed down that part of the question, and we're going to talk more about how that is a very narrow part of the full question. But let's just talk about, for now, the rate of Earth-like planets in the habitable zones of sun-like stars. Now, in this box, you can see the colors. Almost all those points are yellow. I'm sorry for the colorblind people in the audience. Hopefully this is a good color map for you. They're almost all yellow, which means they're almost all M dwarfs. So this was an excellent talk to have immediately after Emily's talk. Most of the rocky planets we have found in the habitable zones of stars are not sun-like stars, they're M dwarfs. You can see one cyany greeny point in the top. That's Kepler 452b, which is as close as we've gotten to an Earth-like planet in the habitable zone of sun-like star. It's a little iffy because it's a bit big and the signal's a bit weak, but that's what we have. But when have we ever let small number statistics stop us from doing something dangerous? Never. So what we do is extrapolate, right? Like we start further up. And there we go. What we do is we start further up and further out on this plot, which is further into the star, and we extrapolate. Now, doing that, we believe that the rate of Earth-like planets in the habitable zones of sun-like stars is somewhere between 10 to 50%. Wildly huge error bars because we have one point, but we're extrapolating. So 10 to 50%, that's not bad, guys. Like given what we know, that's big error bars, but it could have been 0 to 1%. So 10 to 50% feels good. I feel good about that. So that's one of those terms in the Drake equation. Now let's widen this picture a little bit. That was literally just sun-like stars. As Emily so rightly pointed out, 75% of the stellar content of the Milky Way galaxy is in M dwarfs. And we can find rocky planets in the habitable zones of M dwarfs much more easily. And in fact, you can see we have found many more. There's about 14 known rocky planets in the habitable zones of M dwarfs. So we can do better statistics. But these planets, we don't know if they're habitable. And that's the big question, right? Like Emily was talking about, do they have atmospheres? When we talk about the habitable zone is the place where if you had an atmosphere, liquid water could be on the surface. That's really important because guess what's in the habitable zone of the sun-like star? The moon. Does the moon have liquid water on the surface? No, because it doesn't have an atmosphere. All the water just evaporates out. So a rocky planet in the habitable zone of sun-like star is just part of the story, right? So I want you to just keep in mind that there are many more bits to this. So yes, the rate of star formation in the galaxy is only a couple of solar masses per year. The rate of planet formation seems to be quite high. Most stars have planets. That's fantastic. That's really stellar, pun intended. And the rate of habitable zone planets seems to also be high. Those are all really promising. The first half of the Drake equation is like rah, rah, rah. The back half is where it's going to get dangerous. So I'm going to hand it over.
Okay, great. Thank you, Jessie. And Laurie will take it up from there for the first of what are we going to do about F sub L? How do we get life? Where might we find it?
Okay. So I was on travel and didn't have time to make slides, but can we go back to the Drake equation? Okay. So one of the interesting things I think about the Drake equation is it separates out the two variables about is the planet able to support life and is the planet likely to have life emerge in the first place. And this is really important to consider because origin of life conditions, or the situation that could cause life to begin, is not the same thing as habitability. It's more a subset of habitability. And if you think about Earth, habitability is widely varied, right? There's life in all kinds of places. And if you are a lab scientist, you know how hard it is to keep your experiment from becoming contaminated because life wants to live everywhere. But if you do origin of life work, it's actually pretty hard to get it going. And that's because origin of life is more constrained than habitability. And so if we think about what is the probability of origin of life happening on a world, this is actually a lot of questions kind of nested within that question, right? Because yes, if you have a planet where it's habitable enough, you can get prebiotic chemistry, and you can get very simple chemistry, things like meteoritic infall, atmospheric chemistry, oceans, perhaps hydrothermal systems. You can synthesize simple organics, and this is all pretty well known. But then for origin of life, this would have to escalate in varying degrees. So can you get, let's say, polymers forming? Can you get vesicles forming? Can you get polymers to interact with each other? Different types of polymers? Can you get any proto-replication happening? And then at some point, the origin of life community has a bit of the same conundrum as the life detection community, in that we have to define what life is. How do you know when you have it versus just something very close to it? But at some point you have life on a world, and then it can spread and diversify and maybe be detected. And so something that I think is important to think about with prebiotic chemistry is, for any property that we consider a biosignature, meaning that it's unique to life as we know it, how far back in Earth's history does that property go? So let's say oxygenic photosynthesis. It's something that life can do. Not all life does it, but it can. And so, but if you go back in Earth history, that's a few billion years old. It's not at the origin of life. But if you have another property like, say, a membrane, or the use of, let's say, peptides, that goes all the way back to the beginning of life and probably before the origin of life. And so for any biosignature, if you make a timeline of where the origin of life is, does that extend into the past before the origin of life or not? So if that property emerged after the origin of life, therefore, there's a part of life that could have existed without it, right? And if the property extends before the origin of life, then it's possible for that biosignature to exist without life. So those are two things that we have to think about when we look at other worlds, in exoplanets, and in the solar system. And then finally, when we think about the planet as a whole system, prebiotically, you can have prebiotic chemistry going on globally at different levels, but it is possible, of course, for life to have begun on a world and prebiotic chemistry is also still there, because you could have life have happened in one environment, let's say, under some condition, but the whole planet is also a prebiotic world. And it may take some time for life to fully spread and then take over that chemistry. Life right now dominates Earth's organic chemistry, but it doesn't have to. And it's not necessary that the earliest life spreads so quickly. And it is possible to encounter a planet where you have really complex chemistry, something that we wouldn't see today, and it's not alive because it's just prebiotic. So remember that if we're looking for biosignatures, we also have to consider, did any of that occur in the prebiotic world? Could it exist without life? And or could life exist without that if you think it came after the origin of life on Earth? We don't really know. So this is part of what we study in astrobiology and in planetary science with the solar system. We have some good examples of planets with organic chemistry like Mars, Enceladus, and others. And it's exciting to think how we could apply that to other terrestrial planets.
Thank you. I guess one question I'll ask before we go on to Lisa is, as you look at these different environments, particularly in the solar system, as you look to the outer solar system in particular, where a lot of the attention is now shifting, the chemistry is there. What maybe is less available is the energy, the free energy for life. I know people have talked about, looking underneath, the ice shell and seeing what could be in the oceans underneath. How much free energy is there available for life? Just what are the bottlenecks within some of the solar system environments?
So this is a habitability question, really. And so for, let's say, an ocean world, if you want to talk about like redox couples, we would have to have an oxidant and a reductant that life could use. And so in each world, you'd have to look at the abundance of different oxidants and reductants, and you'd have to pick something where there would be a positive free energy in order for life to use that. And I mean, in each world, there are options there. Some of them are better than others. And then origin of life is a separate question, of course. And we have to also think in the past, like what was Enceladus like 4 billion years ago? What was it like 2 billion years ago? Enceladus today is probably not what it was in the beginning, much like Earth. So we have to kind of think about these questions as well throughout the whole history of the solar system.
Okay, great. Thank you. Let's shift to Lisa. We'll talk a little bit about biosignatures in the exoplanet case, which is obviously a much different story than the advantages we have in the solar system.
You can also stop sharing so that you can say hi.
Hi,
Do the-
no worries. We can also say hi later. Thanks so much for having me. And could you get to my slides? I have the ones after Jessie.
Share it again. Here we go. And yes, coming. Yeah, I wanted to show it. Okay, this slide.
Perfect. And so I just wanted to start with this one. This is just a taste that when we think about Earth-like planets, it doesn't have to be a carbon copy of Earth, especially modern Earth, because it has been brought up a couple of times now, and Laurie just went into it, that our planet was very, very different when life originated, and then it went to a point where we could spot life about 2 billion years ago. And so there is a changing features that we can look for in the atmosphere and the surface that could indicate that there's life on another planet. So if you can go to the next slide. So this one actually links what I was talking about with what Jessie was talking about, and tomorrow you'll hear a lot more about the error bars on these graphs, but this is the one from Wikipedia that 3 of my undergrads just made, and there's a paper coming out. So that's basically looking into which planets are within the habitable zone, but also very importantly, which planets are on the outside of this habitable zone that we define. And you see the stars and how bright they are. So we said, like, the M stars, the small red ones, are on the bottom, and the F stars on top. But basically what you see is that most of the planets, as Emily was just talking to us about before, are around these M stars. And so it starts to be critical to actually explore where these limits of the habitable zones are. So yes, of course, we want to find planets that are similar in kind of irradiation. That's what you see at the bottom, how much light they get compared to modern Earth from their star. But it's also important to figure out what those are like on the edge. We call them planets at the edge, and they can tell us much more about where habitability ends or what kind of properties a planet needs to have for there to be a potential water on the surface. And as Jessie just said, it's not a necessary condition that if you're in this habitable zone, you don't have to be habitable. But we define the habitable zone for a rocky planet with about the mass of the Earth, 0.5 to about 10 times the mass of the Earth, could allow for liquid surface water. And so if we go to the next slide, this is a very, very quick overview of what you could look for. And this is a very busy slide, but what I would like you to just glance at, on top, you see the transit spectra of modern Earth. And on the bottom, you see the reflection spectra of modern Earth. And you see very many different features you can look for. And so one of the key points here is that the different wavelengths give you access to different features. And so it is crucial to have a wide wavelength range to actually confirm which features you see. And our best biosignature pair so far, so one gas alone is not going to tell you that there's life. But the best biosignatures features we have so far is oxygen or ozone with a reducing gas. And yes, the star and its evolutionary stage influences very much how these features look like. But there are models out there that you can just download if you want to figure out what's going on, the models and the spectra that go with it in different resolution. But just a key point, since about 2 billion years, that's what Laurie just said, we basically have a biosphere that has changed the atmosphere of our planet significantly. And since about 500 million years, so much, much less than that, we have something that painted the surface green. That's when land plants started to take over the surface. So 2 billion years for atmospheric features that indicate life on our planet, and about 500 million years, so 0.5 billion, for anything that's green.
just so that you can get a feeling for how long you can find these features. If you could go to the next slide, please. And so here you see just the different epochs. Again, nothing in detail, but when you see the epochs, modern Earth is on top, and then and prebiotic, no biology Earth is on the bottom because Chase asked me to be FL, so life. So you see that a planet actually changes significantly the atmosphere from prebiotic to modern. And here you see visible on the left, near infrared in the middle, and infrared on the right. And this is transit spectra, the ones that we can do with JWST. Again, reflection spectra has a different set of features you can see in their different wavelength ranges. But that we will need an HW04 to do it for rocky small planets. But all this is available in case you want to play around with it and see what features you can see. Next slide, please. Here, I just wanted to point out these features so you can see how they change. So on the left, you have the relative reflectivity, so there's the emission, so the reflection really, because we're in the visible. And you see that oxygen starts to show up around 2 billion years ago with methane. So that's the feature of biological life on the Earth. And you see the same here on the transit one, and the indications here are oxygen, so ozone really, and CH4. So it depends where you are, what you can see, and which method you use to find these telltale signs that indicate the planets like ours. And so if you go to the next slide, I promise I only have 2 more. There's one of the reviews that I've written on how to actually look for signs of life with lots of references in case you want to dive into it. And there have been a couple of other amazing reviews. So if you're a student, you want to get started on this, please have a look at the annual reviews. They're usually really great dive off point. And if you want to have a more fun version of it, I wrote a popular science book on it, but go for the reviews, the annual reviews. Those tell you a lot of information. And so the last slide breaks it back together to just saying we have this amazing opportunity right now. We are starting to create a new view of rocky planets. And all of the ones I showed you in the first slide and these ones here are basically the small ones. They all have error bars, and Jessie's going to tell you more about the surveys tomorrow. But what you see here are the mean density lines. And I just want you to look at the second one from the bottom. And so you see that we already have a lot of planets that line in a similar density line as the Earth. So for that kind of mass, you have to have that kind of radius to be similar in composition than yours. But as Laurie just said, that doesn't necessarily mean you will start to be like the Earth. But by having JWST right now in orbit, and by looking at developing an HWO and life concept, and tomorrow you hear a lot more about the future concepts, we have a chance to look at the atmosphere and put the radius and mass and the position of these planets, how much energy they get, in context of whether or not there are signs that indicate life on them. Thank you.
Okay, great. Thanks very much, Lisa. And we'll come back a little bit to talk about, what sort of facilities we might use to actually, detect, life at different stages in the evolution of a potentially habitable planet. But now we will jump to the possibility that we can just join the interstellar internet and directly get the answers to all these questions. Jason, do you want to
Sure.
pick up?
Yeah, I have some site. Here we go. Great. Yeah, so I'll talk about those last 3 terms that Chaz put up from the Drake equation slide, please. Great. So F sub I, what fraction of life-bearing planets might develop intelligence? And one way that we can look to that is whether the development of intelligence on Earth is something that happened once as a perhaps extraordinarily unlikely event, or whether it happened many times. And it unambiguously has emerged many times on Earth, which suggests it's a convergent trait. Next slide. almost now we know that human intelligence is different because we transform the planet with our technology, and no other species does that today. But it is very challenging to find any particular aspect of human intelligence that is unique. And people who study this struggle to find anything particularly unique about human intelligence, except that we have a lot of traits all put together, including our ability to abstract, use tools, communicate tool use to others, and so on. Next slide. So it could be that our special ability to make technology is just that we have a particular constellation of traits that has evolved independently many times. And we just, we drew a flush basically of those traits. A good example of how all of these traits can evolve convergently are mollusks. So the squid and octopi especially, they evolved brains and they evolved tool use completely independently from the vertebrates. So it's not as though these traits evolved once and many species have them now. The last common ancestor of humans and mollusks, if we can go to the next slide. This is a chart of descent of lots of different animals in the animal kingdom. And up in the upper left, you see humans there, 2 stars, because we're very smart and use tools. And we see all these other sorts of things that are representative of different families of life. And the octopi, I have 2 stars there. They have brains, they're very intelligent, and they can use tools. And if you trace our last common ancestor back to what's called the Ur-Nephrozoan, that was a microscopic worm with like 12 neurons. And from that, many different species have evolved, some of them being very intelligent and some not. So it's clear that whatever that creature had, which was neurons, basically, intelligence evolved multiple times in tool use after that. So we think it's a convergent trait. Okay, so what about neurons? Are neurons a convergent trait? Next slide. It's unclear. This is a point of contention in evolutionary biology, whether they evolved once or many times. So we don't know. So it's possible that that's a pinch point. Next slide. But overall, it looks like it could be something that might be quite common. I'll also point out that there's something called the Silurian hypothesis by Gavin Schmidt and Adam Frank that argues that we might not be the first technological species on Earth. We don't have any evidence that there might have been a previous one at all, but their point is that such evidence probably would have completely eroded away or be very hard to find today. So we shouldn't be even so sure that technology has only evolved once on Earth. If it evolved more than 10 million years ago, we might not know it, which is a surprising result. And I know it's been challenged, but I think it's an open question at the very least. Next slide. Okay, so given that, the Drake equation would seem to say that technology must be much rarer than biology, that the first example of a technological species will be farther away, because after all, we take all those terms from the Drake equation, they say that biology occurs so often, we think maybe it's rare, and then the chances of technology evolving after that, even if they're 50%, even if they're quite high, it still means there will be fewer examples of it, so maybe that's not the best way to go. But actually, both approaches are worth pursuing. Next slide. We can't know which is better in advance, but it is very plausible that technosignatures are the better bet, and here's why. Next slide. So first of all, technosignatures might be easier to detect than biosignatures. If you wanted to find life in the solar system and you were at Alpha Centauri, it would be very hard. You could build something like HWO and look at Earth's atmosphere and reflection and try and look at, the atmospheric biosignature gases and say, there you go. But you could also build a big radio telescope and try and detect our omnidirectional radio transmissions, like from the Deep Space Network, for instance. And that would probably be easier. And so I would argue our technosignatures are stronger than our biosignatures, and our technosignatures are only growing in strength, whereas the biosignatures are not in particular. Next slide. Technosignatures could be much more abundant than biosignatures. In the solar system, there are at least 4 planets emitting radio waves. Now, admittedly, the radio waves coming from Mars and other planets that have interplanetary probes are extremely weak, but they will grow with time. And the point is that that if technology can spread, especially if it can spread to other stars, then there's a multiplier that the Drake equation does not contemplate. It's possible that biology is rare, but when it does pop up, it generates technology that spreads through the galaxy. Next slide. Technosignatures could be unambiguous. If you detect that deep space network transmission from Earth, there is no way nature can create that. It is too narrow band for any astrophysical process strong enough to make a signal that you can see over that distance. Biosignatures are notoriously tricky, and we argue about ambiguity about them all the time. Next slide. And finally, it's possible that they could be much longer lived. Biosignatures will last from when they first show up, like Lisa talked about, until the end of the biosphere, which for the Earth is something like 500 million to 1 billion years from now, when it becomes uninhabitable. But it is at least plausible that a technological species could spread to other planets and escape that fate. And if they spread to other stars, they could even outlast the sun itself. And so it's not obvious that any of those things will be true for technosignatures, but it's definitely plausible. And so it's very possible that it's much easier to find technology than biology. So those are my intro slides.
Oh, great. Thanks very much, Jason. Jessie.
Is the Silurian hypothesis named after the Doctor Who Silurians, or were the Doctor Who Silurians named after the Silurian hypothesis? I must know right now.
Yes. Adam Frank is a big Whovian, and he named it after the species in Doctor Who.
Yes. Okay, that makes me very happy. Continue.
So I guess I had a question coming back, to the octopi, whose recent films and documentaries really do indicate how intelligent and how tool-making they really are. I recommend My Teacher, the Octopus, I guess, is the one that's most compelling. But it comes down to, I guess, an ambiguity in the Drake equation, where it talks about F sub I. And I think F sub I or SETI is confusing, and it really is not F sub I.
Right.
It's F sub double E. SETI is the search for extraterrestrial electrical engineers.
I would disagree, but I know what you're saying. And you can still pronounce it SETI.
But it could be potentially a very small subset compared to I, because you eliminate many of the tool-making things. We really are only talking about advanced technology where you've got double E's and quantum mechanics and so on. And that's a very interesting and potentially narrower path than just the development of life or even intelligent life.
Yeah, the F sub C term in the Drake equation is what takes you from intelligence, and we're starting to understand we're not as special as we used to think. It's not as clear what makes that special, but the F sub C is clear. He meant radio waves, like you say, trying to communicate. But of course, today, the search for technosignatures includes much more than just radio waves. We think about atmospheric technosignatures the same way we would find atmospheric biosignatures. And there's search for, we could look for Dyson spheres, we can look for things in the solar system. There are many ways that technology might be detectable. And so F sub C, in my mind, is whenever a species on the planet develops that constellation of intelligent traits that allows them to do something detectable. And that might, as you say, be very rare.
Maybe if I can add something to that, I think another way to think about it is time. And we are limited right now with the 4.55 billion years we have so far. And so if you put that in the 24-hour clock, then life has started roughly around 5 a.m. in the morning, but the biosphere only starts to leave unique signatures, so the combination of oxygen with methane, since about lunchtime, right? So half of the Earth's history, we cannot find the life, even if it was there, because we can't go there. So that's different to what Laurie was saying, where we can actually go to icy moons, drill down, have a look if there's something microscopical, right? And then if you go to civilizations or radio communication, really, civilizations are a little bit older, but radio communications, you're in the last second before midnight. But this is still complementary, as Jason was saying, because biosignatures really interesting and very complex, can be very complicated if they're not like ours. But then if somebody says hi on a radio signal, right, most people will actually agree that that is a civilization that speaks whatever language it is. So I think our time frame right now makes it a small fraction of the life we can be looking for, but a very interesting fraction of a life. And we have no idea how long specific technosignatures will be, right? If they change and they actually become a technology that we don't know yet how to spot, but maybe something is something that we cannot explain, we'll still put in the pot of technosignatures. So I think what's really, really fascinating is to think about time. And as we've seen these planets around these different kind of stars, there's always a time axis in this. Some of them are young, some of them are older, some of them are older than the Earth that we know host exoplanets. So it's really, really fascinating to bring that time aspect in an exploration.
Yeah, and this gives us to the L equation in the Drake equation. If you leave out F sub C and F sub I, and you say the fraction that have detectable biosignatures, then L is how long those biosignatures are around for us to find. And it's important that we know roughly how long Earth's biosignatures will last. We know when the biosphere will go away, but we don't know. We only know how long our technosignatures have lasted so far. And even if you're pessimistic about, the fate of human technology in the future, and I'm optimistic, but some people are pessimistic, I don't think it's necessarily appropriate to transpose that to all the other technological species in the galaxy. I think it's very plausible that that L could be very long, billions of years perhaps, in principle, for technosignatures.
Yeah, I mean, I think there's an interesting question about that L term, the lifetime term. There's sort of a astrophysical L, and maybe Jessie can talk about the lifetime of a habitable planet in an astrophysical sense. Laurie, maybe you could address what you see as the lifetime of a biosphere. And then we get into this question is, what is the lifetime of a technological civilization? And, do we expect lots of little lights in the galaxy, or do we expect to see fireflies popping on and off, and what's that overlap?
Right. Well, so for the first part of that, which is the lifetime of a habitable planet, this is one of the places where M dwarf planets, rocky planets in the habitable zones of M dwarfs, if they are habitable, will have a much longer lifetime in the habitable zone of their star. Their star will have a much longer lifetime. The saying, no M dwarf that was ever born has died, right? The M dwarfs are going to outlast all of us. So, thinking about an Earth-like planet around a sun-like star, we can see the end, right? We know that the sun is going to do its thing and the biosphere is going to do its thing, and that there is a window. But for M dwarfs, that window is much, 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 much longer. And that also gives much, much, much more time for interesting things to happen. So that's one way that M dwarf planets, habitable planets are in the habitable zones of M dwarfs, win out.
I guess,
Maybe
Laurie,
maybe to add, sorry, that it's 100 billion years, right? So it's 100, not 10. It's even more than 100 billion years for M stars. So that's exactly, Jessie, I love your point, but it's so much more than we have.
Right. It's a lot of Ted Lasso reruns is what we're saying.
I guess, Laurie, for you, I guess we want to address both when is T0 for life, which on Earth is actually pretty soon after the Earth formed. And then what is sort of a natural cycle for a biosphere?
So this is one of those things where it's really hard to know for sure because we only have one example. So it's hard to know.
Astronomers, it's okay.
Yeah, well, that's fine. It's difficult because which parts of Earth's history were inevitable and which parts are specific to Earth, we really can't say. So the origin of life did happen, geologically speaking, basically right away. And then life spread pretty quickly, but also the biosphere has gone through a lot of permutations and evolution. And so, I mean, if you think about it, our biosphere, for example, being able to use sunlight as energy and being able to use water as an electron acceptor is huge because it's basically unlimited on both ends. And then you can have a massive biosphere that produces all sorts of things. But it might not have necessarily been the case if you had a different world with different, say, evolutionary trajectory that lets you be able to use certain electron donors and acceptors, or maybe be able to harness light or not, and that sort of thing. And then the origin of life itself, I mean, it seemed pretty fast on Earth, but we don't really know why that is and what bottlenecks existed and whether or not what degree chance really played in that. Because again, you could have a world where you have prebiotic chemistry escalating to a point and it just stays there forever. It's possible to imagine. Or you have prebiotic chemistry escalating and then you have some life, but it never quite diversifies and takes over the way that it did here, especially maybe if you were an ice world, let's say, or if you never had an evolutionary innovation that allowed like the spread of oxygenic photosynthesis or something like that. So I think that it's important to think about kind of speculative other histories of Earth. Like if you imagine rewinding all the way back and starting again, which parts of Earth today would still exist?
So does panspermia play a real role in this potentially or not? Either within the solar system or now we're seeing interstellar comets coming in, presumably with advanced chemistry.
Fred Hoyle has entered the chat.
I mean, I think it's more about the organics that could have come from, say, meteorites and comets. Like, there's a lot of great organic chemistry that can come from meteorites, and there's an inventory there. And then the rocks themselves can be reactive. Like, there might be native metals present in chondrites, and this relates to also Enceladus, right? Because it's a chondrite core that hasn't melted, and so you have meteorite-like material in there as well. So I think more importantly is, to what extent do the meteorites and comets deliver materials to a prebiotic world, and what does that mean for different solar systems?
I would add also that if technology spreads through the galaxy, it's not inconceivable that it could bring biology with it. It's much easier to cover, Mars with robots, but in principle, we could, get some lichens going, add some oxygen. And so if we're really talking about a species that's been around for hundreds of millions or billions of years that could be detectable, it's plausible that that's the most common way that biology pops up in the galaxy, is that it's gardened.
Maybe let me bring it in also to what we said before about the evolution of stars, because we checked now that we know about giant planets around white dwarfs. So that's a paper that's recent, right? But there could be rocky ones. And actually, the habitable zone around a white dwarf would give you about as much time than around the sun to start a second origin if you want. We have no idea if that's possible. But so even if our planet dies or not, we have a high debate going on where these planets come from, probably from further out, blah, blah, blah. But it could all start all over again too, being like completely out there again as I dare. But it's interesting. So the M stars being so long-lived make the chance of finding a biosphere there, if they can hold on to an atmosphere and the life can actually change the atmosphere and the surface, a much better bet for those long-lived stars. And then also the end of the star, or the explosion of the star. So when the star doesn't do nuclear fusion anymore and becomes a stellar remnant, might not have to be the end for our search. And there, the white dwarf is so much smaller, about the size of the Earth, that any biosignatures on an Earth-like planet around a white dwarf would be a whooping signal. And we got some programs with JWST through right now to look exactly for that. Small planets and potential signatures of their atmospheres around white dwarfs.
Okay, here's a question. Any one of you can chime in. There's something called the Fermi paradox, otherwise known as where the hell are they? And there are a variety of very paranoid X-File versions of answers to that. They're there, but we're in the zoo and they don't want to talk to us. If we stick to sort of the science axis, where in that Drake equation is the weak link in the where are they? So,
Not my three. My
So-
three are good. Not the first half.
So I'm gonna quibble. The Fermi paradox asks why there are not aliens here on Earth today. It's specifically about why there aren't UFOs and things like that. More generally, there's this misconception that the galaxy seems very silent. That, we've been searching for 65 years for radio signals and haven't found anything. Where is everybody? But the fact is, we've done very little searching until quite recently. And so today, thanks to Breakthrough Listen, we can say there are probably not narrowband, omnidirectional, always on, megawatt microwave transmitters pointed at the Earth. And we couldn't say that before, but that's a long list of qualifications of what we can rule out for just the nearest stars. the galaxy could be filled with all sorts of technosignatures. We've barely looked. And so I don't think we can say that the galaxy is silent or that there is necessarily even a puzzle to be solved.
I think
Laurie?
another one. Sorry.
Oh, hang on, let's Laurie, any?
I'm afraid
Weak
that
point?
one's out of my expertise. I'll defer to the techno signatures.
Lisa?
I have a different question on that, because the fun part about this Fermi paradox is the inherent idea that we think if somebody could actually see us, everybody would be here, right? That's the underlying implicit assumption that everybody would just want to be here and talk to us. And whenever I ask my students, that's one of the questions I ask in my class, is I say I have 2 planets. And both of them show signs of life. One of them is 5,000 years older than us. One of them is 5,000 years younger than us, all hypothetical. I have the resources to contact or go to one of the 2. Which one do you pick? And 75 to 90% of my students always pick the more advanced one. And so if you just turn it around, if that's common, then why would anybody come to us yet? We have boots on the moon, but we don't even have boots on Mars yet. So Earth being my favorite planet, I would just say maybe we're not that interesting yet.
The only thing I'll add is, it turns out 100 years ago, we had evidence of exoplanets and we just didn't know what we were looking at when we saw it. And now that we know where exoplanets are and how common they are and what kinds of stars were around, we recognize that, oh, that was evidence of exoplanets 100 years ago. We don't know what kinds of life are out there, and that's exciting. But I also wouldn't be surprised if 100 years from now, we look back at what we have and be like, it was there. We just didn't know what we were looking at, because we don't know what kinds of life are out there. So I'm excited by that idea that we have so much data already and we just haven't been able to interpret it the right way yet.
Okay, we have just a few minutes left. So I'd like to see if we have any questions either online or from the audience, if people would like to address a question to any of the panel members.
So this is actually an online question. It's from all the way from it. Sorry, it's from Edgar Munoz Sanchez, and it's directed at Lisa, but I think many of you would have answers to it. The question is, the spectra from Earth's past you showed, were those based on models or inferred from geological or fossil records? Which biosignatures do you consider the most important and most robust for identifying life, and why? I chose this question to read aloud because I think it's important for the astronomers to know just how much we know and don't know about our own planet's history.
I think that's a great question. And this is why I built the Carl Sagan Institute at Cornell, because I think we luckily live in a time where no one scientist can know all the science anymore. So it's critical that you actually talk to somebody who knows everything about geology, somebody who knows everything about microbiology and evolution on the Earth, because these models that I showed you are based on the best knowledge we have about the evolution of the Earth, but it actually becomes more and bigger error bars. Like for astronomers, the further we go away, the dimmer the light, right? The less fossils we find, the less we know about our early Earth. And what's really fun in that context too is that it took talking to a geologist, Rebecca Payne, who was a postdoc in my team, to figure out that actually the highest oxygen content, I should have known that, but I never realized that, was actually on our own planet during the reign of the dinosaur. So if we're looking for oxygen with methane as a reducing gas, actually the planets that could host dinosaurs in space are the ones that are going to be the easiest to find. And we just wrote a paper about that. So you need to talk to your colleagues in the different fields. And that's, I think, what the Michelson Summer School is also so great for. Find people who don't do what you do and learn from them, because that's how we can start to find what the best biosignatures are. And currently, it's oxygen with a reducing gas or ozone with a reducing gas, whether it's methane, that works for the Earth, or N2O. But there's a great review, PNAS Casting 2013, in case you want to know about biosignatures. And for example, out of thermodynamic equilibrium is not a good biosignature, and Jim Casting explains this really well. There's lots of great research that has been done on these things, but we learn every time, and the best way to learn is to talk to people who know something you don't know and discuss.
Okay, question here.
Hi, yeah, I guess this question I'm trying to phrase it correctly, which is, which part of the Drake equation do you find to be more important? Like, would you prioritize a planet that had Earth-like inhabitable zone, Earth-like atmosphere, but a kind of weak biosignature versus one where we wouldn't expect life to be, but there's a stronger like technosignature? Does that question make sense?
I mean, both.
Yeah, I think it comes back to a related question we haven't really touched on, which is making an assessment about whether a planet actually is inhabited requires really multiple data sets to convince you. So for example, you may find, the oxygen A band in some planet, but is that some physical process or a biological process? You may want to know what is the size, temperature, and surface gravity of that planet, so you could rule out whether it's a planet that is currently boiling off its oceans and the oxygen is coming from some, dissociation of water. So one of the things that I think we're focusing on is we're going to take visible spectra with the Habitable Worlds Observatory. If we don't at the same time go to the effort of getting the dynamical mass of that planet so that we can get some idea, is it a super Earth or a rocky planet or whatever? How do we get the surface gravity? We also need the radius. The ambiguity between invisible, between phase function and albedo and radius, is very hard to get a radius. So many years ago, we said, well, we also need to get a thermal infrared measurement from which you can get temperature and radius. So I think the evidence will come over multiple decades with multiple experiments to put all that together to be able to say this planet actually is inhabited with any robustness.
I agree with Chaz, and something I've learned talking to anthropologists, echoing what Lisa said about asking the experts, anthropologists have to distinguish, just ordinary rocks from, things that might be bones, from things that might be technology. And so this is a problem that they deal with all the time. And their go-to technique is context. It's that technology appears in certain, they can say it's surely technology from all sorts of contexts. Where did you find that rock that looks like it was an axe head? What was the provenance? What was around it? And I think it'll end up being the same thing for biosignatures. We'll have lots of good evidence. And then, maybe we will find that there's a whole class of planet that persistently shows this strange feature, and we'll start to understand it from context. But I agree, it's going to take lots of lines of evidence.
And I think it's a great point that Jess you made, and Jason too. It's just like the key point is like we cannot just pick out a biosignature that says life on modern day Earth, put it on a planet we know nothing about or on a gas ball, and then just make the assumption it's exactly also produced by the same biota. And for a rocky planet within the habitable zone, we have multiple models from many different teams. Again, that's critical. More teams trying to figure out how false positives could get generated by geology and by other effects in the atmosphere, for example. And we have to expand that little by little to many planets that might not be as familiar as an Earth in the habitable zone. And even that changed significantly through time. So I think I echoed Jessie. Jessie said she's really excited about the time we live in, and I am absolutely excited about the diversity of planets we find and the things we learn. But as Jess was saying, you need multiple evidence, and you want to have a constraint on the radius and the mass and the temperature, what the infrared would give you, while also the reflected spectra is giving you very specific things of the atmosphere. So together, wide bandwidth is critical. But then also it's the context. You need to figure out what the signal means in context. If this is a biosignature because you understand the geology of that planet, you understand what the flux of the star or the flares do to the atmosphere. So it's going to take a while, but it's definitely not going to be boring.
Fantastic. Thank you so
I
much.
guess what I'd like to do then is end up and give each of the panelists an opportunity to do something which is very difficult, which is to make predictions about the future. So 20 years from now, Jessie, where are we?
All right, so it's 2045. My kids are 30, hopefully out of the house. HWO has launched, is doing its survey. We are finding Earth-like planets around sun-like stars and looking for biosignatures. I'm not sure if even in 20 years we'll know exactly which combination of biosignatures will be the definitive answer. I think we'll have lots of excitement. It'll be like the first few years of JWST. We're just going to argue about interpretations for decades after that, and it's going to be great.
Laurie?
Let's see. For me, it'll be lab research, RNA work. And so I hope that we will be even closer to knowing what the origin of life on Earth really was. It'll be, let's say, we already have made so much progress. Maybe in 20 years, we'll know, was the original metabolism heterotrophic or autotrophic? When did autotrophy emerge and how did it diversify? Which molecules were involved specifically in the origin of life? And what were the order of operations that got us there and what conditions were needed? And then maybe once we know some conditions, we can start to talk about environments, which we really shouldn't be doing until we know the conditions. And then based on that, maybe we can help narrow down some of these variables for the assessment of other planets. Like, it really is very unlikely that life will emerge past a certain point, or maybe it will emerge, but autotrophy is really hard, or. And so hopefully these types of lab work can really integrate well with, say, exoplanet missions and planetary science missions.
Okay, Lisa, 20 years?
I think we're going to be closer to planetary science. Remember planetary science about 30 to 40 years ago? I looked at everything like a small dot and was wondering what's going on, even so the Voyager missions that just launched. And I think in a way, it depends how many smart people we get onto this problem who actually going to interconnectedly work on this, because most of the big questions are the questions at the borders or at the interconnected borders of fields, not in a field. So 2020, best of luck. We still have JWST going. Hopefully it's not going to be the only telescope we have going at that point. Plato's up because that's European. So Heike is going to tell us about this tomorrow. And there's a couple of other. Ariel is going to go. ELT, also European. Ariel, also European. All of these missions are definitely going to go. Hopefully ours will go too. And maybe we can keep JWST alive. And then I think we'll know a lot more. And I'm with Jessie. We're going to be fighting back and forth in the best possible terms about whether this signature is definitely something we cannot explain without life.
Okay, Jason.
So in terms of technosignatures for that, I'm hopeful that in 20 years, it's, spoken of with biosignatures, like on panels like this, it'll just be one more thing we're doing, and that a lot of the techniques will just be, obviously applied to the same things. I think that dedicated technosignature searches, especially in the radio by then, will have been able to say there are not a lot of radio signals, that we'll actually have some real upper limits and be able to say what isn't out there because we're not there. And maybe the reality will match better people's perceptions about how thoroughly we've looked. And of course, there's the wild card. They might have found something. And if you find an unambiguous technosignature, then we get to jump over all of the arguing, right? And just go straight to studying. And then, so I think there's a small chance we'll still be doing SETI, but the S is going to stand for studying extraterrestrial intelligence.
Okay, so I'd just like to thank all of our panelists, and I'd like to invite them all to the 50th Sagan workshop to come back and summarize what we found in the next 25 years. And I think with that, are there any announcements, Elise? Otherwise, let's thank all the panelists.